Hi everyone, the 11.A, the model diagnostics. So the fitting linear model or other statistical procedures is almost automatic these days. As long as you have data and you input the correct code, then you can get the results. So as a statistician, the more important thing is that whether or not that analysis is appropriate. And the model diagnostics clarifies how accurate, how appropriate the model is. So being able to do the model diagnostics is one of the biggest advantage for statisticians. Okay, so this course only covers the basic model diagnostics. So one is residual plot. So remember that we have the model, the y is equal to beta naught plus beta 1 x1 plus plus beta p x p plus epsilon. So the epsilon, we assume that epsilons are independent and also identically distributed. Often we assume epsilon is normal to make the statistical tests valid. So we have to check that. So the one way is the plot epsilon j hat, that is residual observed epsilon, on y-axis, the vertical axis, against predictor on x-axis. Any pattern is detected, then we have the dependence of epsilon j's. So that violates the assumption on the error. So typical case when we studied the univariate, the simple linear regression is that if residual plot has some specific U-shaped pattern, for example, a pattern like this, then so residual is not random, and probably we have to add. So this is x and this is residual. We have to add probably the quadratic term of x to solve this situation. Yeah, so many the possible patterns. For example, sometimes the residual size is larger for large x, and so on. So this also has that problem. And for time series data, so if we think about the yt is equal to beta naught plus beta 1 xt plus epsilon t, and the t is time index, for example, a month or a day, then we have to care about the dependence on time. So of course, here the predictor is xt, but the also important thing is t. So if we take t and the errors, the residuals are, for example, distributed like this. This is typical situation. This is a problem because you can see that the errors are not independent. So if you take the two adjacent errors, residuals, then always this error size is similar. So that means errors are dependent. So basically, dependent observations don't have as much information as the independent errors. So imagine that we have just the 100 independent students, and we measure the average height, then probably that is pretty accurate estimate for population average. But suppose the observations are dependent. For example, we just take maybe all students from the volleyball class, maybe more students are higher than average. So even if we take the average of 100 students, then average height, the sample average height, isn't as reliable as the independent 100 average of independent 100 of students' height to estimate the population average. the population average height of the all students. So these are the necessary consideration, and also the QQ plot. Often we assume that if we do t-test or f-test ANOVA, that we need epsilon that should follow normal distribution. So we have to see if the distribution of epsilon hat is almost normal, and that we can check this in the same way as the simple linear regression, that is QQ plot. Yeah, and some other diagnostics will be discussed in chapter 12.8. So often we skip this in the course because of the time restriction. So QQ plot. So here it's almost the perfect case. So QQ plot is the diagonal, the points are on the diagonal line if the observations are normal. But here you can see, maybe fitting this line, almost all points are on the diagonal line. So this doesn't happen often, but this is ideal case. So typical case that we have these kind of observations. So this is the empirical actual residual. And this is theoretical residual. So some actual residuals are much larger. So that is typical situation like this. So in this case, okay, so some observations are really large. So actually the linear scale isn't really appropriate. So we have to push down so these observations. So maybe the transformation is necessary. For example, we make the y into the log of y or square root of y, and so on. Yeah, and sometimes, okay, so symmetric, but the S-shaped errors or inverse S-shaped error like this or this, then normal assumption is not satisfied. And especially if the tail is heavier, then we have some trouble. So we have to sometimes use different estimation method, even though we haven't covered it. Yeah, but particularly if we have this, you know, the curvature, we have curvature, basically the convex, the QQ plot, then you have to consider the transformation of variables. So sometimes we need a transformation of X, but this is residual, and the residual is basically the Y value. So the making the log scale or square root of scale that is usually appropriate. And also the relationship between X and Y is affected if we transform Y. So sometimes we have to take both variables, the logarithm of both variables or square root of both variables. And residual plot, you can see the weight and the BMP, FE, V1, and RV. These are the variables. So you can say just this is X1, X2, X3, X4. And this is residual, so y-axis. And this should be random. And the error size should not be predicted by the X value. But here, almost the ideal case. Okay, so maybe just a baseline here. And we don't have any pattern. Just the errors are entirely random. I would say this is almost the perfect residual plot. Maybe possibly these errors are a little large in size compared to around here. So maybe we have some tendency like this, but almost we cannot really observe the pattern. So the typical problem happens if the plot is like this or like this time series. And also, yeah, so sometimes the error size is much larger for maybe the larger X. So typical case is, okay, so errors are very small around here, but much larger around here. So that is the case. So usually for this case, we need the time series consideration. Time series model may be needed to remove this kind of the correlation, especially if this time axis is t. And for this one, probably the missing variable, missing maybe x squared or x cubed, or and so on. So that we have to add more variables. And here, usually we need transformation, maybe large x, the larger error for, so probably the log of y or log of x, we have to make transformation. But here, our data shows almost perfect residual plots. And you can see that we have clusters here, but anyway, so x values are the fixed variables. So it's not random variables. So we don't have any problem to have the most observation in here and here. We have clustering, but it doesn't violate assumption of epsilon. So basically the y coordinate, the vertical coordinate is essential for residual plots. Yeah, and these are this is the code for the previous figure. So if you wanna save the plot, our plot in a PostScript file or some other format, like such as the JPEG or BMP, then you can use the function for PostScript, just a PostScript function. And you can specify options such as the font size or the entire width or height of the graph. So this is 8 by 8 inch graph. And some other options. This is also the shape of the entire graph. And then QQ-plot, then the device off, then we finish this PostScript file. And sometimes we have to specify several things. So this is the 4 figures in 2 panes by 2 panes, so 2 by 2. And also sometimes if you make the small graphs, that we have to change the margins so that all parameters can be controlled, and actually you have to control the all parameters. So this is the entire, for example, the PostScript file, and this is the graph. Then we have margins here, 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 here. So these are specified by this margin plot. So this is the bottom, left, top, and right margins. So in this way, that you can make plots just by using code, and you don't have to use the user graphical interface. Yeah. So these are the basics of the diagnostic plots in R. And a little more advanced plot can be obtained by just plot of the LM object. So this returns several things, the residual plot and also the QQ plot and the 2 other figures. And I will explain it in chapter 12 if we have time. But this is the interactive plot. So if you put the enter key, then enter key once, then we will see the 4 diagnostics plot one by one. Yeah, and this diagnostic plot that actually makes the residual plot for the fitted value against residual rather than x1 versus residual, x2 versus residual, and so on. And actually, this is not ideal plot, but the fitted value is, okay, so if we have only one variable, beta naught hat plus beta 1 x1. So this is basically a linear function of x1. So x1 versus residual. So it's almost the same. And if we have multiple terms, then the meaning becomes vague. But at least we see that the fitted value against residual. So if we have some patterns such as increasing variance of residual as fitted value increases, then probably that we need the log or square root transformation for y. So we get some information. Yeah, so just it's not the best, but actually we only have to make one residual plot if we use fitted value. So that's why our outputs only this graph.